Okay, welcome to the inaugural video of the Fred Technical Support Series. This is something new that we're going to try and do, which is take an interesting question that was submitted throughout the week and put a little focus on it in a short 5 to 10 minute video, which we'll be posting to the website and the knowledge base that you guys can then go review on your own time if you're interested in the particular topic. So this week's video came in from the user, and the question was, given that Fred's implementation of analysis surfaces are strictly 2D planar grids, how can I calculate the irradiance on a cylindrical surface? In this case, the user was interested in the irradiance distribution on the cylinder edge of a lens element. So what I've set up here is a simple configuration where I have a point source emitting at some solid angle that should intersect a lens element, including the absorbing cylinder surface that defines the lens edge. And placed in between the lens element and the source is an absorbing aperture, in this case just a simple block. So if we were to calculate the irradiance on the cylinder surface of the lens element, we should see maybe a constant irradiance over some angular range, and then in the region being blocked by the absorbing surface here, we should have zero irradiance. So how do we go about calculating the irradiance on a cylinder surface? Well, here's what we're going to do. We can create a 2D grid in the scripting language. What we're going to do is imagine that we've taken this 2D grid and we're going to wrap it around the lens element so that it's coincident with this cylinder surface. Now we have two dimensions to work with, which means that we can take the x, y, z position coordinates for a ray that exists on this cylinder surface and map them into a simple theta z coordinate system. So each theta z position corresponds to a theta z bin on this 2D grid. In this case, the theta coordinate is measured with respect to the x-axis, so we have 0 degrees increasing around to 360 degrees. Now the z min, z max on the grid correspond to the z depth, essentially, of this cylinder surface. So what we're going to do is trace the rays, and we're going to take their x, y, z coordinates, we're going to transform them to theta z, and we're going to place these in the appropriate bin on this 2D grid. Then we're going to take this 2D grid and place the data into what's called an analysis results node. If you're not familiar with ARNs, now's a good time to become familiar with them, because they're going to be increasingly important in the upcoming releases of Fred. So let me show you what an ARN looks like when it's written to a file. The idea is that the ARNs contain all information about an analysis when it was performed, which means that we can save them to a file or to a node on the object tree in coming releases, which means that I can now store analyses with a Fred document. They know exactly where they were located at the time the analysis was performed. They know exactly what their dimensions are. They know everything about the analysis, which means that I don't have to redo an analysis in a certain configuration when I create a Fred document. If I want to review something, I can simply save it as an ARN on the object tree and review it anytime that I want. So here, let's go ahead and look at the script implementation here. We start off by defining the spatial sampling for our 2D grid in theta z space. In this case, we're doing 90 samples in theta and 50 samples in z, and we zero out this grid. We look at the cylinder surface. This is the absorbing edge of the lens element. We get its x, y, z minimum and maximum. So now we have the z min, z max for our 2D grid. Since we're interested in calculating irradiance, we need to know the pixel area for each cell of the grid. This is simply r d theta to z. Next, we're going to delete any rays that currently exist and trace a new set of rays. Once the rays are done tracing, we're going to loop over each ray in the ray buffer. We establish if it currently exists on the entity of interest, that's the cylindrical surface of the lens element. We get its XYZ position coordinates. These are always returned in global coordinates, so we use the transform position subroutine to convert from global coordinates to the local coordinates of the cylinder surface. We take the arc tangent, y over x, to determine the theta position of this ray on the cylinder surface. And the z coordinate stays the same. Now we essentially integerize the theta z positions and place them in the appropriate bin of our 2D analysis grid. And then lastly, we go ahead and for each cell keep track of its current irradiance plus the power of the ray divided by the pixel area. So that essentially increases the irradiance each time we calculate a ray lying in the appropriate bin. Once we've populated the 2D array with the irradiance values, we go ahead and construct our ARN. So we create that from the existing 2D grid, that's the theta z grid that we just created. We can set its title, the parameters. In this case we have azimuthal angle theta and z distance. And for now we're going to write the ARN to a file. That creates an FGD file called edgeirradiance.fgd. Lastly, we go ahead and grab this FGD file and we display it in Fred's chart view. So let me go ahead and just run that script. Given this is the ray trace, that'll provide some context for the result that's about to be displayed. Let me go ahead and run the script now. And here is the result. So as we can see, this lies along the x-axis. Now we go through theta, and now we're being blocked by the aperture in this region, and then increasing in theta till we return to the x-axis at 360 degrees. So as you can see, this is a short script, 84 lines about, nothing more complicated than taking the arctangent of x over y and assigning that to a bin on a 2D grid. And that's how you can calculate the irradiance on a cylindrical surface in Fred.